So now we will talk about some behavior of a material, starting with ductility and then brittleness. These two behavior mainly represents that how the material is going to work or how it will behave while it is used in or used as structural components. So let's see, starting with ductility. Ductility is the property of a material that enables it to undergo huge amount of deformation or large amount of deformation, which is plastic. That means the property of a material that enables it to undergo plastic deformation after being stressed beyond elastic limit and before rupturing. We can see from this diagram that this stress strain diagram, which is in blue color, it represents the behavior of a ductile material. What it indicates that we know this is our elastic limit. So after elastic limit, it goes to the plastic phase starts and it continues up to the failure. So we can see after the elastic phase, the plastic phase comes up and the plastic deformation increases, and at certain point it reaches the highest limit, that means our ultimate stress, and after that it starts snaking, and at certain point it fails. So this is mainly the property of a ductile material. That means the material which will undergo plastic deformation or which will go a huge amount of plastic deformation, this is our ductile material. And it has some advantages or it has some usefulness because of its desirable property. That means this property is always desirable in a structural material. And plastic behavior is an indicator of reserve strength. That means it will reserve the strength, and it indicates this plastic behavior indicates it as well, and it will serve as a visual warning of impending failure. We will sum up later. Before that, we will go to the another property, which is brittleness. So it is the mechanical property of a material that causes it to rupture suddenly. So we can see from this diagram that at the end of elastic state, just at the end of its elastic state, it doesn't goes any plastic deformation, it ruptures suddenly. So the property of a material that enables it to undergo that enables it to rupture or fail suddenly or suddenly under stress. So the property of a material which is liable for sudden failure will be known as brittleness. So its example may be as the brick. It is actually the undesirable property of a structural material, and it lacks the plastic behavior, thus reserve strength, and it gives no warning sign of impending failure. So why do we need to use brittle? Which type of material is preferable, ductile or brittle? Or why do we need to use, what are the examples of ductile materials? We know the example of ductile materials are steel bars, because steel bars shows, like mild steel, shows plastic deformation before it fails. But in case of bricks, brick will suddenly fail, so which is known as brittle material. So which type of behavior is more preferable for our structure? We know that if load imposes in our structure, and if suddenly or to some extent if it crosses the design load, that means the total capacity of the structure, then it will fail suddenly if we are building our structure with brittle material. But if we use ductile material in our structure, so when load will be imposed in our structure, it will undergo plastic deformation. So plastic deformation means it will, the deformation will be visible. So due to this visibility we will get a warning sign. That means we need to leave the structure or we need to get out from the structure, and this warning or this indication is the indication of failure. So we can easily understand that the use of ductile material will enable us to get a warning sign so that we can avoid any types of collapse or any losses of lives. But in case of brittle material, we know that brittle material fails suddenly. So if we are not using any ductile material and we are building the structure with total brittle materials, we know that brittle materials are lower in cost, but as it fails suddenly, so it will not give any warning sign for failure, and it may cause the loss of our lives as well. So in case of designing a structure, we need to include ductile materials like steel bars or rivers or reinforcements. So these are the mechanical properties. So now we'll see the examples on stress and strain. In example 1, we are asked to calculate or determine the compressive stress and strain in this post where we can see the initial length 16 inch, and we can see it's a hollow section, so it will be having both inner and outer diameter. Here the inner diameter is given as 4 inch and the outer diameter as 4.5 inch, and we can see this entire post is subjected to a compressive load which is 26 kip. So now it is also given that the shortening of the post, so we know that due to the compression shortening occurs or the change in length is negative. That means in compression the deformation is always acts like shortening, or it's negative, so it will act as shortening. So the change in length is given as 0.012. From all this information we are asked to calculate the compressive stress and strain in the post. Now let's find out. So starting with the compressive stress, we know that in order to calculate the stress we'll be needing the force, which is given as 26 kip, and also the area. So as this is a hollow section, so firstly we need to calculate the area. That means we need to subtract the inner area from the total area, or the outer the area considering the outer diameter. So let's calculate the area first. So here is the cross-sectional area. So the outer diameter was, we know that the total outer diameter was 4.5 inch. That means pi by 4 d2 square minus pi by 4 d1 square. d1 is given as 4 inch. So plugging the value of d1 and d2, we will get the value of area as 3.338 inch square. Now using the 26 kip load and area, we will be calculating the compressive stress. We know stress is equals to force divided by area, so we are getting the stress, compressive stress, as 7.79 ksi, which is kip per square inch. Now in order to calculate the compressive strain in this post, we need to follow we need to use the formula of strain, which is change in length divided by initial length. So the change in length is given as 0.012 inch and the initial length is 16 inch. Using these two, we'll get the strain. Now in example 2, we can see an aluminium rod shown has a circular cross section and is subjected to an axial load of 10 kilonewton. That means it's subjected to a 10 kilonewton, and this load is acting as tension or tensile load. Now here also we can see the stress strain diagram of the material. That means the rod is of aluminium. The stress strain diagram of aluminium is given in the question. Now using these informations, we are asked to determine the approximate elongation for this 10 kilonewton load that will occur in this aluminium rod, and we need to consider the modulus of elasticity or Young's modulus of aluminium as 70 GPa. So here we can see the stress system diagram. It indicates that this is the yield point or the elastic limit, and up to this the line is in elastic or proportional limit, and after that the plastic state arises. So if the value of stress crosses this point, then it will be considered as plastic state, and we need to calculate strain using this diagram. And in case of remaining limited in this elastic limit, so if the value in this elastic value exists in this elastic limit, then we will be needing to use the Young's modulus to calculate the strain. So in order to use the Young's modulus, we know that we have Hooke's law, which says that stress is proportional to strain, which is expressed by epsilon, and from here we will be getting stress is equals to modulus of elasticity or Young's modulus, which comes as constant in replace of proportional sign, into this strain. So this is our Hooke's law. So using this Hooke's law, if the value of stress is exist in this elastic limit, that means up to this point, then we need to use this Hooke's law to calculate the strain. So let's check it out. And we also know one more thing is strain is simply equals to change in length. That means the amount of deformation. Change in length is sometimes expressed by delta change in length delta divided by initial length. So now let's calculate those values. So firstly we can see there are two types of cross section. That means one is of 15 millimeter and one is of 20 millimeter. So we need to calculate the stresses along these two cross section separately. So starting for segment AB, the stress in AB will be the load divided by the cross sectional area of AB. That means if we cut a cross section here, so we need to calculate the area first. The area of this cross section will be pi d square by 4. We can see the diameter is given as 20 millimeter. So pi d square by 4, pi into 20 square by 4, and the load is given as 10 kilonewton, which is 10 into 10 to the power 3 newton. We are converting it into newton, and we are getting the area in millimeter square. So we know that newton per millimeter square is megapascal. So from here we will get the value of stress for segment AB, or in segment AB, which is 31.8 megapascal. So similarly we need to calculate the stress in segment BC, load divided by area. If we take cross section in BC portion or BC segment, we will get the area as pi into d square by 4. Here the value of diameter is 15 millimeter. So plugging the value of 15 millimeter in d square, then converting 10 kilonewton into 10 newton by multiplying it with 1000, we will get the total result, which will be 56.6 megapascal, as newton per millimeter square is equals to megapascal. So we are indicating with megapascal. Now we have already calculated the stresses. So from now, considering with the comparing with this given stress strain diagram, we can see that for segment AB the stress is given as 31.8 megapascal. So here is the scale. In y-axis the stress is represents, and in x-axis the strain represents. So the y-axis is in megapascal. So for segment AB, which is the stress is 31.8 megapascal, so from graph we can see that 31.8 is around this portion. So this is in elastic limit. We know that we are considering elastic limit up to this point, as this is the end of proportional limit or yield stress or elastic limit, whatever we may say. So as the value of stress in segment AB is lower than the limit, so is in the limit, so we are considering the Hooke's law to calculate strain for segment AB. So now calculating segment strain in segment AB, we know that from Hooke's law, stress is proportional to strain. That means as we have said earlier, for proportional sign a constant will come, which will be expressed by modulus of elasticity or Young's modulus, and then strain, which is epsilon. So changing the site, we can see strain will be stress divided by modulus of elasticity. So it's simply written here. Now plugging all those value, we'll get the value of strain in segment AB. And similarly, comparing with the diagram, we can see that in segment BC the compressive stress is 56.6. so the 56.6 is around this portion, so it will intersect the diagram at this point. That means it has already crossed the elastic limit. So from here, using the diagram, we will be calculating the strain. So the strain at BC, just taking the value of x-axis, the strain at BC is 0.0450. so we have already calculated stress, and then we are calculating the strain for segment BC. So we just write the strain for segment BC is equals to 0.0450. From the diagram we have got this answer. Now why we're calculating these strains, we know that strain is simply equals to change in length. Change in length is denoted by delta and divided by initial length. So the change in length delta will be equal to, if we change the site, delta will be equal to strain into initial length. So as there is two segments, one having 15 millimeter diameter and one having 20 millimeter diameter, that means one is segment AB and segment BC. So we need to calculate the change in length or deformation for AB and BC separately, and we need to then add those things up. So that means we need to do summation. So we can say that simply for segment total rod, we need to sum up the segments deformation or change in length. So summing up the the result of strain into initial length, we can get it as 0.00045. that means the strain in AB section into the length of, we have got the strain in AB section as 0.0040045, and the length of AB segment is 600 millimeters, so we are multiplying it with 600. And then for BC similarly 0.0450 into the length, which is 400, so 400. From here we will get the total change in length for this segment, which will occur in this due to this load of 10 kilonewton.